let's crack on with it. Were you here yesterday? Um,
I wasn't here
no.
yesterday, no. I was skiing.
Oh, sure. Yeah, okay. Nice. Sounds like a lot of fun. But okay, so today, last week for this one, we were doing some probability stuff. Um, Again, given that Unit 3-4, some people are still doing, or an upcoming integration SAC, I'm happy to field questions for any of that stuff. But I've also noticed a lot of schools have either moved on entirely and done it, or part of their revision time is also front loading the probability stuff. So as a default, I'll be going through the probability stuff. If there's anything specific that you guys want to do that's more targeted to what you specifically want, then then we can focus on that instead. And yeah, just another disclaimer for anyone who wasn't here yesterday. I've been dealing with a sickness for quite a while, and I am very tired and lethargic. So if I make mistakes, if I do something that sounds incorrect or looks incorrect, it might not be your understanding. It might be the fact that I'm a bit out of it today. Things went well enough yesterday. I don't think I made any errors, but again, just a heads up. Okay, cool. Let's begin then. So we introduced a little bit of binomial last time we finished. We had done up until the end of discrete, and then I talked a bit about how binomial is a subset of discrete probability, where discrete probability basically has outcomes that have a discrete, like a specific number of possibilities. For example, rolling a dice. You can only roll the numbers 1 through 6. You can't roll a 1.5 on a dice. This is what we refer to as discrete. Binomial is a subset of that. That's even more specialized, where as part of the name, it looks at possibilities, or it looks at probability scenarios where there are only two possible outcomes for your experiment. So the classic example would be a coin toss, for instance. Heads or tails, those are two separate outcomes. There are other criteria here, which essentially just sort of boil down to the fact that every time you repeat the experiment, in, for example, the coin toss, the probabilities should not change from trial to trial. That doesn't necessarily mean they should stay 50-50, or they have to be 50-50 from the get-go, but it does mean that whatever they start out as can't change from trial to trial. Essentially, whatever you've done in the first repetition of that experiment, you have to now reset the board and then go from the start again. The list here is just a few key terms that you can look at and use that to clue you in on whether or not you likely have a binomial distribution. These ones are the clear, obvious ones. They use the word binomial in it. This one may be a little bit less obvious, but this is the mathematical notation for a binomial experiment. Keywords like independent, replaced, returned, these kind of mean the same thing. Fair trials, which means basically you do the same thing over and over again, nothing's changing from trial to trial, this sort of thing. So, how do we calculate binomial probabilities? Technically speaking, we can calculate this the exact same way we do discrete probabilities. We just look at the number of desired outcomes and then divide by the number of total possible outcomes. This is true of all probability no matter what. When it comes to binomial specifically, so long as you can identify the three key parameters, you can speed things along quite rapidly. Because one of the things you'll run into with binomial probabilities is your sample space gets quite large. Like even tossing a coin 5 times in a row, that's going to be 2 to the 5 possible outcomes. What's that? 2, 4, 8, 16, 32. That's already 32 separate outcomes. And so trying to think about which of those 32 you want might be a bit tricky. better instead to identify what the three key parameters are. It's going to be the n, the p, and the x. So n is going to be the number of trials. It's the number of repetitions that you're doing of the experiment. That's going to be given by this statement here. The coin is tossed 5 times in a row. Coin is being tossed, and because it's being tossed 5 times in a row, the experiment has been repeated 5 times. N equals 5. Next up, the p-value. The p-value is essentially going to be the probability of the desired outcome occurring, or what you'll see usually referred to as the probability of a success. In this case, it's kind of irrelevant which one you pick because it's a coin toss. It's 50-50, whether you pick heads or tails as your success. It's kind of whatever. But in other circumstances where the probabilities do differ, obviously you want to make sure you're choosing the right one. So as a good principles approach for it, if we look at the actual question that's being asked, what's the probability of tossing 4 heads? This makes heads the desired outcome, and therefore your p-value is going to be whatever the probability of a single success is. What's the probability of tossing a head? Lastly is x. X is the number of desired outcomes you want to have happen. What is the probability of tossing 4 heads? X is therefore going to be 4. You'll notice that all the terms in our equation are now accounted for. So we plug them all in, simplify our results, and then whatever we're left with is our final probability. Any questions about any of that? One of the things you'll often do is use a tech active approach when you do your tech active exam. There is a very quick way of implementing or achieving the Bernoulli sequence, this equation, and it's just found in your CAS under the probability menu. So if you have a look at the document camera, if I go to menu under probability, open that one up, you go to distributions, and then it's all the way down here at A. Underneath it is a very similar thing, which we'll look at in a second. The one you want is the PDF, probability distribution function. If you want to see what that looks like, again, you'll just see what's your n, what's your p, what's your x. So he'll fill out exactly what we had a look at before. N equals 5, p equals 50%, x was 4. It'll always give a decimal by default, even if you do have your CAS in exact. The easiest way to chuck it back to a fraction is to just grab a copy of it and then it'll autocorrect itself. Any questions there?
Sorry, what did you click to make it not a fraction?
Yeah, so I basically just grabbed a copy of it like you would for any other thing that you try to reuse, and then just hit enter again.
Okay.
Because that'll default back to using exact. Cool. Okay. Next up, we're going to learn about how or what the CDF is used for. And this is where you're trying to find a range of probabilities. So pretty much across all of the probability area of study is going to be split across finding individual probabilities of specific outcomes and probabilities that cover a range of possible outcomes. Probabilities that are looking for a specific outcome are referred to as PDF functions, probability distribution functions. Questions that require a range of possible outcomes, they use the notation of CDF, cumulative distribution function. So, here's some of the key things to watch out for. Because you're dealing with discrete here, but there's only a few possible outcomes here. There can only be very specific results. Everything is separated by an integer. When you have less than symbols, whatever your upper bound is or lower bound is, whatever it is, you want to round inwards. So if you're doing x is less than a, whatever is one value less than that boundary is what you use, because you're non-inclusive of that upper bound. Same thing over here. Because you're greater than a, you do not include it, and the next value afterwards, therefore, is the next increment up. Joined a few minutes late, but did we look at the explanation for the formula? Like back to the Bernoulli sequence one? Did you need me to repeat that? Yeah, sure, we can do that. So, let's think about what each of the terms in the formula are actually doing. That can maybe help to identify like what this massive mess is. Which, by the way, you don't actually have to have this memorized. I didn't mention this last time. This will be on your formula sheet. Although it's a little bit weird how it's presented. You actually have this split across two separate sections, which is quite strange. I'll show you what I mean. Okay. Alright. Where have we got it? VCAR. Pretty sure this should have it. So this is technically equivalent. What you'll notice is that all the factorials have kind of disappeared here, and they've replaced it with these sort of like matrices kind of like brackets. The rest of this is the same, and to remind yourself what this is, they've just redefined it up here. Kind of weird. I don't understand how they were running out of space. Do you reckon they were running out of space? I mean, geez, maybe even just put the whole thing in here. Yeah, I don't know, whatever. Point is, it's in two separate spots. So, what do each of these terms do now? For those who have done counting methods somewhat recently, you guys might recognize this. This is the NCR equation. The counting methods area of study is basically all about counting the number of possible outcomes given some sort of parameters, right? And the NCR equation that you see highlighted there just so happens to be one that fits quite nicely with the parameters of binomial. So that big term there, you can think of as calculating the number of total outcomes. Yeah, number of total outcomes that you could have. The next couple of terms are weighting that by the relative probabilities and the number of successes / fails you want. P being the probability of a success and x being the number of successes means that this term is weighting the number of successes you want. So if you have big one of these, this is going to get bigger. Well, the overall thing is going to get bigger. What you'll notice is that this is inversely proportional to this. As p gets bigger, this 1 minus p will therefore get smaller. Therefore, this term here, if this ends up getting bigger, this one here is tracking the number of fails, basically. So we got number of combinations, weighting it by the successes, weighting it by the fails. So for instance, probability of tossing 4 heads, well, that's 4 heads, so 4 successes, and because we tossed it 5 times, therefore there should now be 1 more fail. It's written as n minus x, so you don't really have to worry too hard about that, so you can literally just calculate it, but this is the way you need it, or you could think about it, which is why when things simplify down, you'll see, yep, probability of success, 4 successes. Probability of fail, 1 fail. That's basically the gist of how it goes. Do we need to revise how like the factorials work, or is that good enough? Cool, okay. Alrighty. Okay, so what I was getting on about here was the specifics of discrete. So remember that like x is the number of desired outcomes you want. It's the number of successes. And you can't have half a success. That's just not really a thing. So that's why these can only be incremental values. They can only be integers, right? Separated by plus minus 1. So any less than or greater than signs, you have to round inwards. Any inclusive, you just choose whatever the boundary is itself. As for how this is achieved tech-free, let's have a look. Again, we've got a coin being tossed 5 times in a row. We want to calculate the probability of tossing 1 or fewer heads. The way we do this is similar to how we do discrete. The lowest number of successes is obviously going to be 0. So when you have less than or equal to 1, the sum of those parts is going to be 1 and 0. 1 success or 0 successes. It's the exact same way you handle the discrete for the probability distribution tables that we looked at last time. What that means for us in binomial is that we do 2 separate Bernoulli sequences for each of these, and then just add them together. We do a Bernoulli sequence for x equals 0. These ones usually come out quite nice. X equals 1 also usually comes out quite nice. The factorials, like x equals 0 pretty much deletes the entire thing. And x equals 1, you're pretty much just left with the numerator. So they're quite nice numbers to have. And they'll usually do that in a tech-free because I don't want you spending too much time doing too much math for that sort of thing, given that really what they're trying to do is test, and as long as you can do at least one of those, well, that's enough. And then yeah, you got your 2 results. Thankfully they are same denominator, so you're just going to add them together and then simplify. That's the tech-free way of doing it. Any questions there? Yep. Random question, how reasonable is it to do really well in tech-free, considering haven't done well in tech-active SACs, which have been super hard? Tech-active is usually harder than tech-free. So we see that typically across the board, that tech-free is easier, or you get higher grades than tech-active. At least that's definitely been my experience also in my school when I did my studies, and also from what I've seen across the board for most students. As far as SACs, again, there's going to be differences from schools, of course, though it's quite unlikely that... I mean, I've seen a lot of different schools do different things, and yeah, it's typically across the board that the tech-free will be better than tech-active. Average SAC scores were cooked because they were hard. Yeah, so if you do really well on the exam, they will scale up. Yeah, absolutely. And yeah, as long as you're consistently, and you're consistently attending classes, you're always looking for advice, you're getting questions answered, it's good stuff. You'll do better than me. I hope so. because you had a lot more support than I definitely did. You get to learn from all of the mistakes I made. Okay. Now for the CAS thing, the CAS syntax is effectively identical. It's in basically the exact same spot. In fact, not only that, but technically speaking, you could even just grab a copy of any binomial PDF you've already done, and you can just put a C in front of it. Now, that does require you to know the actual syntax of what to put in the thing. I'll just do this for a quick demo, and then I'll show you what the more appropriate way of going about it would be. Okay, so it'll be something like that. So far, this is just the exact same, and it's going to be add B. So menu 55B would be the fast way to get there. Binomial CDF. Give it a click. You'll see it's effectively the same thing. You now just have two X's. One's the lower, one's the upper. Number of trials was 5, if we remember. It's still a coin toss, so 50-50. It was less than or equal to 1, so the lower bound is going to be 0, and the upper bound is going to be 1. And again, if you don't want the decimal, just grab a copy of it again, and then hit enter. Any questions about the CDF? Actually, I'll add one thing, which is in Tech3, they pretty much limit the CDF to only ever evaluating 2 outcomes. Again, this is for saving time. You're never going to have to worry about doing too many. Yeah, you're one of many who have praised the probability bound reference. It's one of those things where, because probability is basically exclusively problem solving, like none of these questions make it. I mean, like if you do enough questions, of course, they become obvious what you have to do, but there's all words there, basically. Like, yes, there's numbers, like little digits in there, but it's one of those things where there's a high learning curve, so I was able to put a lot of time into thinking, well, okay, what are the ways in which probability topics interweave with each other, and just trying to simplify the whole thing down into saying, okay, if you have these key things in your question, it's going to be this section of probability. And because it's this section of probability, here's the things you should be looking for with it. Here's the parameters for that thing. Now that you have its parameters, look at your equations. Can you slide them into the equation? So that's up there for everyone, by the way, in the probability section. So have a look for it. It's the one that definitely got the most praise, for sure. The others, not so much, but those are still useful. But this one, so far. Yeah, Taihan?
Yeah, is it a good idea to do kind of like practice X or practice questions with the bound reference from the start, or more to try without it?
It's up to you. If you're going to have a bound reference that has a bunch of questions in there that you want to reference, then it's a good practice to practice how to reference them. What I would suggest is just know what are the key things you're unfamiliar with, and you'll know, right? Everyone will know what the main things are they're unfamiliar with, and maybe just like highlight those or star those in the chapter section, so you know how to quickly get there. And yeah, feel free to practice using those on the textbook questions. Totally up to you. As long as you're, yeah, should be fine. It'll be either that, or maybe try the question first. If you get it wrong, then look at the bound reference portion of it. Because if you're getting it right off rip, then you might just not need the bound reference for that. But that's personal preference there. I think there's not too much to be gained either way. Or at least there's no major advantages either which way. Okay. This is now what I mean by why they limit CDFs, or how they limit CDFs to two possible outcomes. Just 1 second, just drinking. Which is, you might get a question that says, hey, find the probability of x being greater than or equal to 1. Problem is, they didn't give you anything to do with n. And so, actually, is this one that, wait, which one did they not have? Oh, I didn't, this is a later, yeah, okay, sorry, that's a later one for a CAS question. Okay, that'll be later. For now, we'll just say, okay, cool. If you're trying to find probability x greater than or equal to 1, and you know that your n is 5, hypothetically, that could mean, okay, I've got to do a PDF for x equals 1, x equals 2, x equals 3, x equals 4, x equals 5. You don't want to do that tech-free. That's a bit ridiculous. So one of the things you can make use of is complement probabilities. Again, we saw a lot about this in the distribution table. Basically, if you think about like a number line, x greater than or equal to 1 on a number line from 0 to 5 would just mean from 1 to 5. Which means the only thing left would be the x equals 0. So, if this is one portion and this is the other remaining portion, and all probabilities need to add up to 1, then you can use complement probabilities to greatly limit the amount of, of calculations you have to do. It's a very common one to get tech-free. Specifically, x greater than or equal to 1, maybe x greater than or equal to 2. So we're going to use exactly that, and rather than having to do, what was it, 4 different CDS? 5? PDS rather, we only have to do 1. And it's an easy one, because when you go backwards, the numbers are easier to work with, so it's even better that way as well. And the result that you get should make sense as well, right? There were 5 different outcomes one way, and then only one, the x equals 0, the other way, so it makes sense that the one that has the more outcomes has the vastly bigger probability of occurring.
Why do we only do the 0 probability and not the 1 also?
Yeah, because this one is inclusive of the 1. So basically what you want to look at is whatever this is what you're going to block out. So if I pull up the notes bit, the document camera rather, let's see. And we have our number line of possibilities. We have x equals 0, 1, 2, 3, 4, 5. X greater than or equal to 1 would be this. X greater than or equal to 1. What you're looking for is the complement to this, which means everything that is not this. The only thing that is not that is just x equals 0. If instead it was x just greater than 1, you would have this instead, x greater than 1, and therefore the complement would now be this. Is that a bit clearer?
Yeah, makes sense.
Sick. Okay. So yeah, that's how you do that one. Now for... this is the one that I don't think I ever got in school, for sure. There's a few of them like that in school that I didn't get. And I remember when I was first starting tutoring, this is one of the things I had to write guides on pretty quickly. Because there is technically a CAS option for this that can quick solve these. It's called the inverse binomial. It's used for solving binomial probabilities where n is the unknown, but you know your x and you know your... actually, it's not even that. It's there's a couple of parameters. I've played around with it. I personally just don't get my head around it. You guys might be able to figure it out because you're probably smarter. But I never got my head around it, and so I've made basically an algebra way of going about it instead, using the same sort of stuff you already understand, and then melding those tools together. So, why is this a complicated question? The probability of winning a game of chance is 0.25. So essentially, like let's say it's a dartboard thing. 25% chance to hit the dartboard, 75% chance to miss the dartboard. 2 outcomes, binomial. What is the minimum number of games that must be played? So, it's asking you the minimum number of games, n, to ensure the probability of winning is at least twice is more than 0.9. I didn't write this on myself. I pulled this from either a textbook or an exam, simply to show you that the wording of these is not particularly pleasant. So there will be a learning curve here. The easiest thing to rip out of this is going to be the 0.25. It's going to be your p-value, probability of winning. From there, because it says what is the minimum number of games, you know that n is the thing you need to find. Probability of winning at least twice, so getting 2 successes. Probability x being greater than or equal to 2, at least 2 or more. That probability of winning at least twice needs to be more than 0.9, 90%. Big mouthful. So when you're going through it, you pretty much just try to start and see if there's anything easy you can rip out of it, which is going to be the p-value. Look for like a what statement or like a find statement, and that'll tell you which one. And as you see these more often, you'll notice just by the wording itself that you don't even really need to read it too hard. You just kind of notice it as a question that is this type. They don't really word these any differently or rewrite them with different parameters. Sorry, not different parameters, but like different tricks necessarily. So you can, once you do enough of these, you'll start identifying what it is. Excuse me. Okay, so as I said, number of trials are unknown. And because number of trials are unknown, when we're doing x greater than or equal to 2, our n could theoretically be infinite. It's not gonna be, but we don't know when to stop writing. So the way to go about this is to do a complement probability. X greater than or equal to 2. The complement to that is the x equals 1 and the x equals 0. From there, fill out each of these. In fact, you can even Bernoulli sequence these yourself on the CAS, and I believe it works even if you put in the letters themselves. So you don't actually have to do this, I think. You don't have to do this algebraically. If you just do the tech active way of going about it. Come on, CAS, turn on. Cool. Which would be the binomial PDF. You would have your n, number of trials, being the first thing, and you write that as n. From there, we were told the probability of success is 0.25. Yeah. And the desired number of outcomes for the first thing would have been x equals 0. Come on. I'm sure it worked before. Okay. Bugger. Maybe I did something different. Oh well. So maybe you do have to do a bit of the algebra instead. Which isn't too bad. You're just working with n's instead, but again, they're going to limit it to x equals 1s and x equals 0s, which, as I said before, x equals 0 completely kills the binomial coefficient at the start. You can see how it disappears entirely, no coefficient on the exponential term. And the x equals 1, you're always just left with whatever the numerator is. So as long as you follow those rules, this stuff shouldn't be too hard. You're removing practically all difficulty, and you're just doing relatively easy stuff like 0.25 to the power of 0, or 0.75 power of n. Similar thing going on here. We now have our two outcomes, so we're just going to shove them in the brackets and do our 1 minus. It's here where we now do our CAS solve, and one of the things you're going to have to watch out for here is, even though it's said to solve for more than 0.9, the CAS doesn't like it. It just sort of bugs out. And so what you're better off doing is making it equal to 0.9 instead, and control entering. That'll get you your approximate solutions. It will always only ever be an approximate solution. You now have two possible values of n. N is the number of trials that you are running for the experiment. So one of these outcomes, no matter how you round it, is going to come out poor. That's going to be the negative that we remove. So the only thing that's left is to say, okay, is this n equals 14 rounding down, or is this n equals 15 rounding up? So the rule for this is you do always round up in this case. Under SAC pressure, under exam pressure, you might forget that. In fact, I wouldn't trust myself either, whether to round up or down. And so one of the things I would do, rather than go straight for this CAS solve, is actually define this as its own function first, and then CAS solve with it later, because once I get my solution, I can now plug in that n value, right? It's this should say f of n. All those n's will be replaced with either 14 or 15, and you just test. These are supposed to be probabilities. If we wanted to be greater than 0.9, this one is pretty damn close, but not quite. Rounding up to n equals 15 is the way to go here. It's a very complicated question. This is probably where we're going to focus the most of the lesson, unless there's anything you guys want to specifically look at. Is there any questions so far? How to find the function? Refresh the whole question again. Yeah, okay, cool, that's fine. Okay, so defining the function, I guess we'll do it live together for this then. Oh wait, no, I think I just remembered how to simplify this now. I think it's the NCR. Let me see. Magnify 3 n comma 0. Does that work? Yeah, what a stitch up. Like, the binomial PDF uses NCR, so for some reason putting an n in there causes it to crap itself. So putting an n in the just the coefficient bit works itself out nicely. There we go, that's what it was. So these will always be tech active, so that's a nice little good thing that I remembered. Alright, so from the top. One second. Jeez. Okay, so from the top we are looking for the parameters that we already have access to. Probability of winning a game of chance is 0.25. So we're going to put in p equals 0.25. It's then asking, what is the minimum number of games? So n is the unknown. I can't put a question mark in here, otherwise the CAS will break. What is the minimum number of games that must be played to ensure the probability of winning at least twice? Winning at least twice therefore means 2 or more successes. So you want to have a probability x greater than or equal to 2. and you want that probability to be more than 0.9. The final probability to be more than 0.9. So the thing that is going to matter for the beginning is going to be identifying the p-value and identifying the PR x equals something. That's how we then start out our set of equations. This will always be done with complement probabilities because since n is the unknown, you don't have any possibility of going upwards, right? You don't actually know when to stop. You can guess and check, which actually is another way of doing it that is kind of fast. But we'll work on this one for now, just so you can use similar principles that you've used before. Yeah, and so complement probabilities means we send it back down to the x equals 0, x equals 1 stuff. So we're just going to do each of those Bernoulli sequences. So we'll do our NCR n comma 0. Explain how we got to the first equation. Yeah, just 1 second. Yeah, first equation. So the leading part of it, x greater than or equal to 2, is from this statement here, probability of winning at least twice. So you see this wording here. Tossing one or more head is the same as winning one or more times. Similar idea to geez, it's quite slow. Similar wording to one or fewer heads, so winning one or fewer times. So that gets us the first part of that equation. Geez, I have something really stuck in my throat. Okay. Cool. So that's going to be this first part. Then from here, because we understand that n is unbounded, we have to now do the the reverse, right? Because we need to cap this off somehow. So that's going to be the x equals 1, the x equals 0. All right, going backwards. This is x greater than or equal to 2. Everything that's opposite is here. So from here, we can now use the CAS to simplify these. We're just doing Bernoulli sequences. So we need the NCR term multiplied by the probability of success to the power of successes. So if we're starting with the x equals 0 one, this will be power of 0. And then the complement to that, 0.75 to the power of number of fails, which would therefore be n minus 0, or technically just n. Oops, that's not a 0. Which gets us 0.75 to the power of n. Then once you've written that again, it's quite nice because, oh geez, well, if you don't do that, it's quite nice because all you have to do from this point is change where the x, or what the x's are. So every instance of x equals 0 now becomes x equals 1. From there, we need to be adding these things together. And then we end up with that. Did I make a mistake there? Something about that feels off. 0.25, 0.75, and take 1. Maybe they did some factorizing. Yeah, okay. Oh, right, and then I've got to do 1 minus. Yeah, because we found the portion that is to the left. Now, because we're trying to do complement probabilities, it's always 1 minus, whatever that is. This obviously looks a lot different because the CAS simplified it and factorized. We're just going to go with it. We now have our equation. Any thoughts about that? You came off mute, but I didn't quite hear what you said. Next up, we're doing our CAS solve, or at least maybe we should first define the function itself. So defining h of, I guess, n this time. That way we can make use of it later for a bit of error checking. It also makes your CAS solve a bit nicer. We wanted to make sure our probability, the final probability of it, was greater than 0.9. We're going to make it equal to 0.9 because if I don't, the CAS will complain. We're going to Control Enter, and we're going to get the same results as we have there. Just to show you what the CAS, actually maybe I shouldn't, because I'm pretty sure the CAS like freezes, and we don't want to waste that time. Okay. That gets us our two outcomes. From here, you're pretty much just obviously eliminating this, and all you want to do now is figure out what the rounding on this is. This is supposed to be a number of games that you play, and you can't play a decimal number of games. So we're just going to test which of these give the desired outcome, which 0.91 belongs to the n equals 15. It's tough. I'll show you a different way, because I think this will be a thing that you get once you run it back. Maybe once I have the energy to post the recordings. And so here's another way that has nothing to do with algebra, and it's pure guess and check. And it makes use of the fact that, okay, we don't know what n is, but because I have a CAS and I have a CDF, you know, CDF being the range of possible outcomes, I can technically guess and check my way through this. Number of trials, I'm just going to hypothetically say, well, I already know what the answer is going to be, so let's just pick a smaller number. Base probability of success here was 0.25. We wanted 2 or more successes, so that will be a lower bound of 2, and then whatever you chose your n as will therefore be your upper bound, because you're going from 2 to whatever your absolute max is. So whatever you're guess and checking with, you do that. Whatever the outcome is the probability you get if you run this experiment 6 times. From here, maybe just try 8. How does that work? Alright, we're getting closer. What if we try 13? Alright, pretty close. What if we do a big jump? Get all the way up to 16. We might have went too far. Let's roll it back a bit. 15. Still a bit above. Maybe we have some more wiggle room. And there we go. We figured out the breakpoint. That's faster. I still think it's nice to understand the concept of how complement probabilities work, because it does help you if you're tech-free related stuff. And being able to understand equations on this level in terms of variables and complements is nice. It's a nice skill to have. But this is also pretty good. Definitely faster. Anyone need clarification on how that's worked? Okay, I think as a bit of a proof of concept, let's see if you guys can do the guess and check yourself. Because once you know how to do it and identify what all of your key parameters are, should be good to go for those kinds of questions. It's all of the 14C stuff. Finding n, sample size. They give you a logarithm thing. I do not like the logarithm thing. This is what they oh, yeah, okay. And this is the other way they showed, which is what we were discussing before, right? Getting our Bernoulli sequences set up, making it equal to our target probability, solving for n, rounding, that sort of thing. I think my camera just buggered off, really. That is in... Jeez. Let me try to pull that in while I pull up a question. We talk out loud what we're looking at. Okay. Okay. Are these all going to be the same thing? Probability of a target shooter hitting the bullseye is 0.2. Is that the p-value? Shooter takes 5 shots. That's already n. So nope. Ah, here we go. So again, what is smallest number? What is smallest number? What is smallest number? Minimum number? Fewest number? You know, whatever that is going to tell you that it's this kind of question. So that immediately gives you the idea. From there, you'll notice that the probability thing is going to be the easiest thing to... Whoop, double audio. 1 second. Just bringing the camera back in. Hey, it's back. Nice. Yeah, and then if we look at the other ones, right? So, probability of success, probability of hard center, probability of winning, probability of hitting the 4, you know, just different words of saying probability of success, basically. Probability of desired outcome. That's going to give you your p value. So if we're doing it for question 3 here, what's our p-value going to be? Okay, well the p-value is the base probability of success, which is going to be the probability of hitting the target of 0.6. So that's going to get us p equals 0.6. If you guys lost the pin of the camera, it's back up now. If you just have a scroll through, you can repin that. Okay, next up, minimum number of shots. That's again the wording that implies this kind of question. Probability of hitting the target exactly 5 times. So hitting exactly 5 times means exactly 5 successes. In other words, x equals 5. If it's said 5 or more times, or more than 5 times, then you're doing greater than signs and so on and so forth. From there, that probability needs to be greater than 0.25. So probability x equals 5 has to be greater than 0.25. How we're going to do it is via some cas playing around. So because we're doing an x equals thing rather than a range of probabilities, a domain I guess to say, we'll do the guess and check through the PDF. Again, we don't know what n is. Let's just start with 10. We knew our probability of success was 0.6 and the x value was 5. Already that's 0.2, which is fairly close. Maybe we'll increment that by 5. That's even closer. Maybe we'll do it by 2. That go down? Wait, what? Oh, right. This is one of those things where, because it's an x equals thing, it doesn't actually consistently ascend. Yeah, that's actually kind of funky. So for the x equals ones, you definitely got to play around a bit more with the guessing and checking. Oh yeah, I misread this. That's 0.2, that's 0.02. Okay, cool. So the less number of trials we have, the better. There's a minimum of 5, of course, so let's go with like 7. Looks pretty good. We'll go up, because that seems to lower the probability. Okay, apparently I just don't know how this works. So we'll just keep guessing. Really?
Is it 7?
Yeah, but I'm trying to find like a upper or lower bound. Because yes, it's 0.26, that is above 25%, but there might be another number that's closer. But it does say minimum number, and we did just try 6 and 8. So yeah, I think it's just going to be 7 here, because it did say the minimum number, not necessarily the number that gets you closest to 0.25. So yeah, good call.
Yeah.
Okay, that was definitely a roadblock there. It's not usually the case I do these for the x equal stuff. Yeah, exactly. At least twice. Yeah, let's do one for the inequalities. Okay. Probability of winning a prize in a game, so p equals 0.35. Fewest number of games, winning at least twice, so x greater than or equal to 2, more than 0.9. That's going to go back to our CDF. Number of trials, again, let's just give it a go. 10. Probability of success 0.35. Lower bound. What was that? So great, yeah, at least twice, so 2 or more. And then you just choose your upper bound to be whatever you made your upper bound. I got it pretty close. Now we'll just walk it back a little bit, just to see if we overshot it ever so slightly, which we actually hit it quite nicely. So n equals 10 is going to be your answer there. We'll do at least one more. If anyone is keen to give a shot, let me know. I'll just find one. Yeah, okay. We'll have a look at 6. Anyone want to give this one a shot, or should I finish this one up myself? Okay, no worries. So hitting a 4 has a probability of 0.07, that's our p-value. Fewest number of balls, so again, just tells you that this is the kind of question. Hitting more than 1 4, so that's a non-inclusive of 1, it's more than, not more than or equal to. And that probability has to be more than 0.8. So, once again, let's just leave the upper and lower as they were before. The p-value is going to be 0.07. Yeah, 0.07. This was the lower bound, which means more than 1, so that's still just going to be 2. Huh, that's convenient. Okay, we're way off. Still pretty off. You tend to also need to make bigger jumps as you get further out, because binomial distributions have a center and they sort of taper off at a certain point. So you can see how the jump from 9 to 30 did a lot more than the jump from 30 to 60. Maybe we'll do 55. Oh, right, we're looking for 0.8, not 0.9. 50. Okay, maybe a bigger jump. 40. 45. Uh, 0.8. And then, yeah, we just slowly walk it back. 44, 43. So it's a bit of a mindless approach to it, but it's probably better than trying to, or easier than trying to get your head around the algebra for it. So maybe start with this one, and then if you're interested in the underlying algebra, then you can go for that, just for better understanding. Okay, cool. Usually I have time to stick back. I'm really feeling it now. I need to rest. And so if you guys do have questions, like, just message me and I'll get back to you maybe by tomorrow or so, or even maybe like end of tonight when I've had a rest. But yeah, I appreciate you guys sticking through it. Yeah, thank you for coming.
Thank you.
Cheers.
Thanks, Chris. Hope you get better soon.
Yeah, thanks.